Yes. Yeah, good afternoon, everyone. Welcome to our distinguished speaker seminar series. We are Women in AI, organization of NSF AIH Institute. We have 3 student members, and I am Jiayu Mao, and other 2 are Ala Vadadi and Dabashri Roy, which are all here today. And we have also like 3 faculty members, Professor Julia Saferglu, Professor Yinbing Liang, and Professor Jim Cruz. Today, we are very pleased to have Professor Janise McNair as our second distinguished speaker. Now, Anna will take over.
Hello, everyone, and thank you, Jiayu, for your introduction. Today, we are honored to have Professor McNair as our panelist, and it's my pleasure to introduce her. Professor McNair is an associate professor at EC Department of the University of Florida. She was a pioneer in early next generation mobility management for cellular system, and she's currently a researcher in the development of multidisciplinary cross-layered network systems. In her current research, she applies software-defined networks and machine learning principles to create adaptive telecommunication infrastructures for physical systems, including agriculture, remote construction sites, and smart grids. Today, she is going to talk about secure smart grids. Professor McNair, please feel free to get us started.
Great. Thank you so much for the introduction. And thank you very much for inviting me to the AI Edge Institute. Very exciting things, multidisciplinary and advanced research going on with the Institute. So I was very happy to come and speak to this group. So today, as you mentioned, I'm in a variety of areas myself, trying to get more into multidisciplinary research. So I will talk today about my smart grid research. Allow me to share my screen. Okay, does everyone see the correct screen?
Yes, okay. That's correct. Thank you.
Great. I thought if you didn't respond, then I'll assume that's correct. Okay, so as I mentioned, I'll be talking about smart grid security. So cross-layer intelligent cyber-physical systems for smart grid, which will encompass the physical power system, the network system, and analyzing all of it will be this AI machine learning type infrastructure. So first I start out a little bit with background about the smart grid. It turns out that this, we've been here before and we're back again. So back in 2005, there was a big push for smart grid infrastructure, updating what we had. I mean, the electrical grid that we have goes back to the 1900s, early 1900s, and is largely a patchwork of systems developed across this country, at least. And I think similar to other countries where there's a need to sort of connect technologies and connect systems, but anytime you connect these disparate systems, there are issues with compatibility, upgrade, investment in the resources, and getting everyone on the same page when everyone has an independent system. So as I mentioned, in about the mid-first decade of 2000s, we had Congress in this country move to say, okay, we're going to make this investment. This is an important research area, so we will start making an impact in this area. However, these practical things that I mentioned a moment ago came into play, where the smart grid technologies were accelerating, but at varying rates across the country. And the cost of deployment becomes an issue. If you're a small city or a small township, you may not be able to get the same technology and equipment that a large township would get. Or maybe some people were concerned about the technology itself. You'll see the fourth bullet, cybersecurity is an issue, privacy is an issue. So skeptics may say this is not something we want to do, and then jump into this internet style of power communication and be open to all of the hacks that are involved with that. So the government funding kind of slowed down around 2010 through 2014. and then really by 2017, so that the funding to implement sort of a widespread grid was way below what the estimates of what it needed to be. So the other institutes like the Electric Power Research Institute and the Brattle Group did investigations of how much do we need to invest versus how much the US government was investing, and they weren't matching up. So smart grid research in general slowed down for some time during those years. However, at the same time, sort of a grassroots movement was coming up where people were more interested in electric vehicles. People were invested in environmental policies and how that was affecting their local community. And people were getting more oriented towards customer interfaces and real-time pricing programs and individualized service as it came to services from the government or services from multimedia, entertainment, etc. So even though people were lagging in terms of infrastructure and skeptical in terms of security, people were actually being trained on some of these other technologies to be more accepting. So the smart grid came back, basically. It hasn't gone anywhere, but it's had a new, breathing a new fresh air in terms of funding. Getting my clock so I can watch my time. The funding now is growing again. So there's estimating the smart grid market to rise to 140 billion by 2028. And these re-energizing efforts will actually serve to put in the infrastructure that's needed to make this a grid itself, a connected grid where many people can enjoy the benefits of having this grid. So grid modernization is moving away from this large scale generation, monolithic generation points that were centralized and delivering to the community or to the city, into more of a distributed approach with renewable energies that can be generated, end user segments that can participate in a variety of ways. And then you have sort of a multi-faceted, multi-option operation for the smart grid, where there are lots of options for generation, not just a monolithic power plant, but people can generate at home. Businesses can put solar panels on their buildings and generate energy. As you've seen many of these things before, the windmills, the water distribution, all those things. And also the electric batteries, lithium batteries that cars use, and just that generation of energy around the grid that didn't exist before. So this delivery is distributed, and now how do we incorporate all of these options into our plan for this smart grid that goes across any country? Now, we've done much better in Europe, and especially Germany and some other places, to implement the smart grid. I think even Australia has made significant progress, but here in the US, the feet have been dragging a little bit. So at the same time, we're developing a closer and closer smart grid technology. Smart grid communications becomes more of an issue. Cyber security is always a factor in no matter what we interact with these days in terms of entertainment, healthcare, education, etc. So it's also an issue with a smart grid. So this Power magazine in 2019 talked about the dark side of the smart grid, that cybersecurity is an issue, and they had a speech by the chair of cybersecurity studies at the Naval Academy. He described the cybersecurity problem as stemming from the interaction of the people who defend themselves from the attacks. If their sophistication is rising, you can kind of meet the attack. One example might be people know to run antivirus software, or people know to protect their passwords, the things that people have learned to do automatically just to protect themselves. So the sophistication of the defender is rising, helping reduce the attacks. But on the other hand, as the attacker sophistication rises, then the attacks become more of a force to deal with. So it's a dance that happens between the attackers and the defenders to see which one is on top at a given time. Another example of this is the two-factor authentication, where people say, okay, if I'm going to log into my account, I put in my password, the system sends me a text, and then of a code number, and I enter that code number. Well, attackers figure out that if I can get that person to give me the code number, then I can get in that person's account. So attackers may call someone, tell them their account has a problem. Can you try to log in? The person tries to log in, and then they get the code. And the person on the phone, the attacker says, can you give me that code? Then I can see if your account is correct or not. And if people are not sophisticated enough to realize that they're giving away all of their information, then they may give the code, and now the attacker's in anyway. So there's a dance between how much people are used to doing to protect themselves and how much the attackers have figured out to game the system. So there's an entire research area to study the robustness of systems. One of these studies was by Jin, which used to be at the University of Florida, and he discovered a whole bunch of security holes with the Google Nest family of systems. In particular, since we're talking about power, the Google Nest thermostat was cracked or hacked, and they were able to not only receive the privacy information of how you're using your power in your home, but also control your thermostat to change the conditions in your home without a person knowing about it. So, did I hear a question? So these happen on a much larger scale as well, bringing it back to the smart grid system. We have an attack surface. Oh, I didn't read that quote. So this idea of number 3 is that the size of the attack surface keeps growing. So even though you may be sophisticated on how to defend in one area, there may be another area that needs defending as well that we're not quite up to speed with. So that gives people pause when we talk about making an entire grid that's based on cyber information and cyber exchange and smart grid communications. Here are some examples that are not helpful to propagating this idea of smart grid. On the left-hand side, there's this malware called Triton that attacked a specific equipment company. This company, Schneider Electric, made controls-oriented equipment for utility companies. And because the equipment was controls-oriented, that meant that the hackers, if they could control this equipment, then they can control the power plant and cause it to shut down or cause it to produce too much energy, etc. So it's been experienced around the world. They've been experienced in the US, in the Middle East, and other places around the world, this Triton group. In 2016, Ukraine experienced a power outage that was assumed to be initiated by the Russian Sandworm hacker group. And this group actually, as I understand it, interfered with the sensing, the power state estimation system, which regulates how much power is delivered to a given area by collecting how much power is being used, comparing it to the normal amounts, and then if it's over, then you cut back. If it's less or not enough power, then you send more. So one way the power can be cut is to send the message that there's too much power being generated and none of this power is being used. So these users don't need this power that we're generating, so let's cut back. The hackers sent false data saying that we'd have enough power, nobody's using this additional power, cut back, until the system cut into a blackout and resulted in 80,000 customers being without power. So this was all done with a cyber hack, and they didn't have to physically go disable these utility systems. So as we talk about this resurgence of the smart grid, we also have to talk about how will we identify these attack surfaces and protect them from not only just hackers, but protect them from faults, from natural occurrences, and yes, from hackers inserting false data into the system. The smart grid security is a multidiscipline challenge that involves cyber physical system that's looking at physical measurements, taking some analysis of them, doing a feedback loop, and then taking some actuation in the environment. It's a heterogeneous and complex system. So I mentioned a lot of different inputs into the power system that have different types of renewable or traditional energy sources, and lots of links for connection between systems. And then managing these networks using traditional schemes increases the cost, because now you have a custom hardware solution for every case, which may not be necessary. We would rather have an adaptable software-based solution. So power system, networking, and cybersecurity. In addition, artificial intelligence, as it relates to the AI Institute, can be employed to help us figure out how to detect these security attacks in the presence of sort of a random system of power system measurements. So this is related to a project that I did with my colleagues at the University of Florida. Arturo Bretas is a person in power systems engineering, and I'm in networking and systems, and I do some security in networking. And then Alina Zaire is an expert in machine learning and AI at the University of Florida, also working at the UF AI Institute. So we have this project and several different sub-projects on separating this power system into several layers. One meaning a physical domain and collecting the physical information, and the second being a cyber domain that monitors the cyber activity of the network. And then the third one's not shown here, the machine learning or analysis domain, where we process the data that's coming from the other layers. So here's a more simplified version of that diagram. We have the cross-layer cyber physical security framework. And this framework has as several elements the same things I talked about before, but a little more explicitly diagrammed so you can see each part. The physical layer has the, sorry, I'm setting the timer to make sure I don't go over time. The physical layer has the devices that are deployed for power use in the system, and from those we'll take power system measurements. And it has the power measurement units that are monitoring the physical system on the bottom. These power measurement units are collecting our sensor data or measurement data that's necessary to monitor the system. This measurement data goes up to a cyber layer in concept, where state estimators and controllers exist to toggle the amount of power that's distributed for a given system. These PMU nodes, or power measurement unit nodes, are also part of a data network that's exchanging the state estimations and exchanging data to determine whether sort of a wide variety of things. One, whether there is attack or a fault, or more energy is needed or less energy is needed to be generated. So this entire network is shared by the PMU units as a normal communication network. Each PMU node has some operation in the network, this software-defined network operation. It has some machine intelligent elements and the measurement unit elements. The top layer is the software-defined network layer. It's a distributed layer because this, as I mentioned, is sort of heterogeneous, patched together smart grid network may not be a centralized controlled network, but we may need to provide distributed control. In addition, with a distributed SDN, we don't have a single point of failure for our system. So our software-defined network we'll talk a little bit more about later, but the job of this layer is to monitor this PMU network and determine if there's any network anomalies that occur on the PMU network, as well as implement and control the network itself As an example, if this PMU node at the bottom right is exhibiting that it's been attacked, or maybe it's just faulty, then the software-defined network can cause that PMU node to be unincluded in the routing path, and that node is no longer allowed to share data. Using our design software triggers, we can do this without having a human intervention. So this can immediately happen once the SDN is triggered, causing this PMU node to not be able to affect the other nodes of the network. So our problem has been isolated until a human is able to investigate and see what's happening with the system, fix it, or take away the threat, and then it can be integrated back into the network. So let's look at some of these systems that we've diagrammed here. So remember, there's a power system layer, the machine learning, and the network management. At the power system layer, we have real-time system monitoring. So there's a SCADA network that some people may have heard of that implements the monitoring control for the power system measurements that are being sensed on the electrical grid. It's centralized now, but I think it's evolving as well to become a more distributed system. But for the context of this first study, we assumed it was centralized monitoring and control. After the measurements are taken from the system, there's a pre-filtering, or before the measurements are taken, there's a pre-filtering process where measurements that are completely off are discarded. So if someone's generating, I don't know, 20 kilowatts in a neighborhood or in a home, and it's the middle of winter and everyone's running their heaters, but you're pulling like 1 or 2 kilowatts, then that doesn't make sense and it doesn't correspond to a valid data. It might be an error caused by a glitch in the system or a faulty meter or something that's generating some bad data. So all of that data is clearly inconsistent with historical data and is disregarded immediately. It's the pre-filtering process. In the power system state estimation, we have the collection of relevant power grid information. So this becomes more of a macro collection of data and comparison to make sure things are consistent across the network. This figure on the right, I couldn't find a source for this figure. If anyone knows, please let me know and I'll put the attribution here. This figure represents another vision of the PMU network where they're all connected within the transmission network and also report back to the control centers. So we've filtered the data, filtered out the outliers. Now we have our set of power system estimation data. Now we can post-process it. Once we've collected it, we try to detect if there are any gross errors within what we've processed to see if there's statistically large enough change that we need to investigate further. So a pre-filtered measurement is something that's way out of bounds. A gross error is something that could be a real scenario, but just may be an abnormal scenario. An example is, let's say, as I mentioned, let's say the World Cup is happening that day, then all the power from the people in restaurants and at homes will shoot up, and that would be an abnormal reading. But if you look at the events of the day, then that could be a realistic reading. So concerns for interconnection and dependence include the idea of being a part of this smart grid and what will happen to my system as a result of me being connected and interdependent on the other systems. So it raises concern to false data injection. So as I mentioned with the Ukraine example, if someone inserts some false data, you can cause the power system to behave a way that's unexpected or unintended. In false data injection attacks, a subset of measurement values are modified and then inserted into the network to disrupt the grid. There's also bad data analysis. So in bad data analysis, you have these tests that try to figure out if the data we are reading is realistic or if it's something that's being inserted or created by a defunct device, for example. So we have tests, as I mentioned, in the power system for these gross errors to detect something going wrong, but we can improve this and leverage this for cybersecurity by implementing machine learning techniques as well as network security techniques to see if these are failures in the presence of cyber attacks. So here's the power system again, another version of it. You'll recognize the PMUs here. This box, this box, this box. These are all instantiations of the PMU that would be communicating together. The satellite represents a GPS system that's monitoring the PMU locations. The cloud here that's monitoring the data is represented, but in this figure, we more want to represent how the PMUs are connected to the neighborhoods and the neighborhoods are connected to the backbone network. In previous work, we looked at the extended chi-squared test and used that as a basis to determine if there were gross errors within our power state estimator. We used a correlation detection algorithm that we call CORDET to figure out if the gross errors are present and if there's a need for further action. This is also a way for the machine learning process to start recording what is normal data, what is abnormal data, and begin to classify how the data is behaving. For this simple approach, the threshold was not adaptive. We just set a chi-squared test and a CORDET algorithm based on a given threshold. And we could not use time-varying load scenarios. As I mentioned, different things happening in the neighborhood on different days and different seasons. In the workday, usually nobody's home from 8 to 5, but lots of people are at home around 5 or 6 to eat dinner, or 7 or 8 people are waking up to go to work. So there's lots of variation in the power drain in a given suburban neighborhood. And it didn't incorporate the network level considerations. As we'll talk about a little bit later, if you have a power subsystem that's under attack by a hacker and trying to enter to change these data readings, then that will have a signature on the network itself. So if we watch the network in parallel with the power system, we can maybe correlate whether these events are happening at the same time and then recognize an attack versus just a random error. So walking through one of our analyses, this is how we came to connect our machine learning algorithm to our power system estimation process. So as I mentioned, we can use different means to measure this error. In this case, we used the weighted least squares and modeled the system as the measurement vectors we're receiving from the power system. And the measurements processed by this H value to model the changes in those measurements, plus the error measurement vector. And that's a zero mean Gaussian random variable. We wanted to form a best estimate of the state vector, this J Jacobian matrix, or J, this H is our Jacobian matrix, as the mean square error of this comparison of the measurement vector and our model of the actual real measurements. This form allows us to form the covariance, this covariance matrix of the measurements is included and allows us to form this Jacobian matrix H operated on our states or measurement states X and leaving our error as part of the sensed state Z and trying to determine how close delta Z is to delta X. Let's see. these delta Z and delta X represent the current state estimate versus the historical state information, and the current measurement versus real measurement versus the estimated measurement, and the current historically and the current estimated measurement. So this statistical chi-squared test is used to compare this J matrix to the chi-squared parameter, and we determine if J of X is larger than a certain value, then an error is detected in the measurements. We extended this a little bit beyond the chi-squared measurement by using machine learning techniques to identify anomalies in our error measurements. So this is the same slide I showed you before, talking about false data injection, bad data analysis, but now we're just going to incorporate our machine learning technique. So here we have the correlation-based detection algorithm that I mentioned before. We're going to look at the incoming sample and identify if it's abnormal or normal based on its Mahalanobis. I know people just say Mahalanobis, but I just realized today there's an H in there. So the Mahalanobis distance with respect to the background statistics. The measure of Mahalanobis distance is just used in statistics to figure out if something is an outlier compared to other data. For example, if you're looking at a field and you're taking images, you may be able to detect a landmine by determining this Mahalanobis distance and showing that this is an outlier compared to the rest of the area. Our machine learning options we considered were neural network methods, which are straightforward for infrastructure, but the parameter adjustment is not easy. We could use deep learning, but that carries with it a more complex training method. We could use unsupervised learning, and that's not as rigorous as the other two, but it provides initial weights and you can back propagate the errors to fine tune your model parameters. So we found that to be the most useful technique for our application. And here in calculating the core-det or the correlation detection process, we have our Mahalanobis distance here, delta CD of Z, from the, if you recall, that's the given data that we receive in our power measurement unit. And the mean, calculate and compare that to the mean of the distribution. Let's see, so we take K incoming samples that have not been flagged by the state estimator as abnormal, so they're presumably normal samples. We generate the initial mean and covariance matrix as a starting point, and then we accept new data and start using the historical data to compare and determine if there is a Mahalanobis distance that indicates an abnormality. So this threshold value tau allows us to compare the Mahalanobis distance. If it's greater than tau, yes, there's an abnormal outlier present. If it's less than tau, then we consider this to be a normal data value. That will now allow us to label this data and also to gather the training data within the machine learning process to figure out how we're going to label different events. So just based on this one approach of taking in the power system information, applying this machine learning process, and evaluating according to the status of the data, enabled us to improve on the current state of error detection in power system networks. These graphs at the top are comparing the recorded measurement values in our system, our emulation system, compared to the machine learning values in our algorithm. So in most cases, our machine learning residual values were able to detect this FDI, false data injection attack, as an abnormal outlier within a set of data. And you'll see that these peaks identify that an attack is taking place. This peak is located between 4,000 and 5,000, just like this peak here and this peak. So the measurement and the analyzed values were coming up with the same result, which is always great. So we did an analysis of the precision of our measurements, the recall, the F1 score, to see how often we hit the correct value, how often we avoid false positives or false negatives, and how close our value is to the ground truth, and found that we did very well compared to just the normal technique used in power system measurements. So this is our state estimator from related work and our presented Courdet technique. So 98% to compared to 97%. So we had some victories and we had some losses in terms of our scheme doing better or worse in terms of precision and recall, but our F1 score was consistently better than the old state estimation scheme that was previously used. So in forming this correlation detection method for one set of primary or power measurement units, we were able to determine whether that one unit had some outliers that indicated it may be under attack. We decided to extend that concept into what we called an ensemble Courdet, where our primary measurement unit grid of a network of PMUs can now be separated into clusters. And each one of those clusters can do its local Courdet test to see if there are outliers in the system, to see if there is an adversary in that particular system. But at the same time, we send that up one layer of hierarchy to do an ensemble Courdet to see if the network itself is under attack. Often when one part or one device is being compromised, there's an attack in other parts of the network as well. So we can use this information in our machine learning algorithm as an indication that, yes, our network is under attack and needs to be quarantined or isolated. And these are the particular points that are indicating this attack. So the next step, and this, sorry about the fuzziness of this diagram, this one's much better. So now we add the network layer. As I mentioned before, way back at the beginning, you may not remember, I'll go back here. So there's a physical layer that we talked about, the power measurement units. There's the cyber layer, the machine learning elements that analyze what's happening in the system measurements. And now we'll talk about the networking layer that will help us also indicate with more certainty if the power system is under attack. Okay, so now in our ensemble Courdet analysis, we have individual clusters of machine learning algorithms happening to evaluate what's happening at a particular power measurement unit. Then we take them as an ensemble collection of information to evaluate how the system is performing. If we get an indicator from any of these units or clusters that there is a problem, as I mentioned before, we can isolate that unit. And how do we do that? We do that using software-defined network control, which is a new paradigm that allows access points and switches and routers to update their routing policies based on software and not depending so much on hardware. The hardware becomes more of a forwarding process and all the intelligence is pushed into software, which means it can be adaptive, it can change things on the fly according to different algorithms. So what we decided to do at the network layer, not only do we do the software-defined network control, but we also, pardon me, look at, as I mentioned, I think before, the layers of attacks. So if someone's initiating an attack on the power system using the communication system. The communication system will detect an attack at the same time, adding validation to this attack event, and also adding more information to the machine learning infrastructure of what an attack should look like. So we looked at three main types of attacks. I already described the false data injection, which happens largely at the physical domain and the smart grid layer. But there are also denial of service types of attacks that can repeatedly send information that's meaningless, but when you send it at a high rate from a lot of different nodes, then it can crash your system. It can also be a result of affecting the data that's output from your smart grid system, so it will result in altered measurements. At the cyber domain, or the communication network layer, the denial of service can render the network performance statistics to be different, or as I mentioned, it crash the system so that no information is coming out, which will alter what's being received by the Coordate algorithm, or in the current state systems can alter receiving any state estimation information. And then finally, man in the middle, when we talk about false data injection, often a device is becoming a part of the network that wasn't intended to be a part of the network, and it's receiving information on one hand, inserting information on the other. So from the networking perspective, this sounds like a man in the middle attack that we can implement in our simulations and see how that impacts our ability to detect what's happening in the power system. So the cyber domain usually looks at the output in terms of network performance statistics, the time delay, inter-arrival time between packets, and the type of packet data that's going back and forth. With all of these sources of information, we now can make a cross-layer ensemble Coordate with adaptive statistics to make a more complete machine learning process that includes all three of those layers I showed. Plus, it's now an adaptive process where you don't have to fix on one PMU and one threshold value. So I'll just sketch through this. I know we don't have much time left, but the idea behind being able to control the PMUs and decide new policies and new connections comes back to this idea of autonomic virtual networks. So one of my PhD students worked on this architecture and implementing this SDN relationship with different nodes and implementing machine learning modules that result in a change in network policy. So that's what this architecture is all about, but we won't have time to go through a lot of this architecture. So I'm going to sketch through some of these things that we've studied. So the first thing we did was to characterize different attacks in terms of network behavior. We've seen this before in different areas. We wanted to do it for the power system. We can identify anomalous traffic, specifically for denial of service, that DOS stands for denial of service, by looking at clusters of traffic and comparing them to other clusters of traffic to, again, see if there's an anomaly. We examined various characteristics of the traffic, such as the destination port. If there's normal traffic, it's usually consistently going to the same few ports at the destination. If it's an attack, then you'll see some variation in the ports in a patterned way that you can see. Obviously, some things ramping up these port numbers, and why would something do that if there's a random connection? Looking at the destination IP addresses, normal traffic again, usually networks send to the same few destination IPs. If there's an attack, there may be some unrecognizable destination IPs or a strange variation of them. Packet features may change, length of packet or different contents of the packets may change. And packet feature, this is the variance, this is the mean. The mean picks up a little bit of information, but the difference, it may not be large enough to indicate, as well as these destination ports and destination IP graphics do. I will skip through this one. It's another part of anomaly detection, but this time for the traffic. We also tried a multivariate Gaussian distribution approach to look at our network data and use this analysis to find peaks that indicate when these, where in the data set these anomalies have occurred, and demonstrating something that is not normal in our network. Using both of these techniques, we were able to gain some strong information in terms of looking at anomalous groups in our data traffic compared to normal traffic. The pros are it detects greedy bandwidth application and can successfully prevent flooding with denial of service, but it also can confuse greedy bandwidth with some slow rate denial of service. So in other words, something is attacking your network by sending too many packets, but they're not doing it all at one time. They're slowly trickling in the packets so that you can't identify this rush of information. It's more of a slow rate, but still the volume is still encroaching upon your access points or nodes. So then we implemented this clustering technique to, I'm watching the clock, so I'm almost finished, to try to do more of a sliding window approach to figure out where the attack is happening, even under slow rate attacks. And it was successful in being able to pick up the slow rate attack detections. I won't go through this since we're almost done, but just suffice to say, we looked again at collecting packets from a data set that was made available to us of an actual network traffic, then analyzing the flow, the TCP exchanges, the inter-arrival times, the packet features, and using this, we were able to detect both slow rate and flooding denial of service, but we had to look at other techniques for other malicious attacks. So here, just solely on detecting networking attacks, our clustering method did very well for accuracy and precision, not so well for sensitivity on all of our techniques, but in terms of specificity, precision, and accuracy, did very well. Okay, and here's another graph for that. This is just comparing for different data sets that we used, as well as the normal state estimation, the Cordet, the ensemble Cordet, and the ensemble Cordet with adaptive statistics. This last one includes all three of those processes I mentioned and has a very successful hit rate in terms of getting accurate, precise, reliable, and high F1 score in the results. So just wrapping up, we have a test bed that we're putting up at the University of Florida that's based on a virtual power grid that has emulated data from real power systems. It has emulated control system of, I think, IEEE 118 smart grid or power bus, and is able to emulate having virtual measurements from the PEMU units and the SCADA network. And on our side, we have a virtual communications network based on Mininet, and also we're using SIM components and other Python programming to generate network data and compare that in parallel with the IEEE 118 bus, and then be able to run our machine learning algorithm on top of both types of data. So in summary, multiple levels of interconnections, multiple levels of intrusion, multiple attack surfaces. So when looking at any cybersecurity issue, especially cyber physical security, we need to consider the various attack surfaces, and all of those surfaces will give us information in terms of analyzing and classifying what kind of attack has occurred. So we're developing new CPS methods to address these problems, and this ensemble Cordet technique has shown very promising results. We've published these results in many different places, so at your leisure, you can look through some of these publications and read up more on this topic. That's all for my presentation today. As you can see, there's a lot of information. I tried to distill it down. I'll open it up for questions. Any questions? I can't hear anyone if there's anybody asking.
Excuse me, may I have a question?
Yes.
Oh, yeah. So have you ever tried to use some deep-based clustering algorithms, except the class one like K-means?
So what do you mean by deep-based clustering algorithms?
I mean
So-
the clustering, yeah, deep clustering.
In terms of collecting the data about the packets and the packet features, etc., deep clustering.
Yeah.
I don't think we've used that to this point. We may need to investigate that and see, compare the results versus the complexity of implementation, but it sounds like a promising approach.
Oh, okay. Thank you. Yeah, because I ever heard of some training for the deep learning based clustering algorithm, but I'm very curious about that. Thank you about that.
Right. That's something my students can investigate. I think for these early studies, we kept with more tractable solutions that we thought could be performed online, but I'm not familiar enough with the deep clustering techniques to let you know if that's something that would apply here or not.
Thank you so much.
Thank you. Any other questions?
Hi, Professor. I can ask one question. I'm wondering, like you mentioned in the soft, where like you managed to generate some data and then compare with IEEE standard. I'm wondering, like, yeah, how do you generate those data? And I'm curious about why you generate data by yourself if IEEE already had some. Yeah, thank you.
So I think we did a combination of both actually to implement this study. I'll show you this last test bed slide. Here. So we are, part of the data input is the IEEE record of packet exchanges and network behavior. I think the former versions of these smart grid networks had some capabilities, but didn't have other capabilities, had some communication techniques, but maybe not as modern. So we take the data that's generated by the PMU units, then we can put it into our emulator to show how it would be exchanged in a modern network. So the data that's being collected from IEEE is based on the power generation system. Then we put it into a PMU network, as would be a more modern system. And we use those packet exchanges also looking at them on the communication side of the PMU network. So we use the data, but the data doesn't give us the network statistics or the PMU exchanges that would occur as a result.
I see, that makes sense. Thank you.
You're welcome. Okay, looks like there's some more questions. Kai, I saw you unmute. Were you about to ask a question? Okay, maybe not.
If there's no more questions, let's close today's discussion. Thank you, Professor Janise McNair, for your very interesting talk, and thank you everyone for your participation. Our Women in AI organization will invite other distinguished speakers later, and please pay attention to our advertisement and join us if you're interested. Thank you very much.
Thank you. I had a great time.
Thank you.